All right, folks. Do you want to see what an unhealthy obsession looks like? This is it. For about the last month or so, I've been rapidly prototyping and iterating on a half mask respirator design that can be autoclaved or sterilized with solvents and cleaning solutions. During the course of this project, I basically bootstrapped myself from knowing zero anything about molding to printing complex multi-part molds with undercuts and casting silicone molds so that I can cast urethane parts so that I can overmold silicone on top of it. So this whole project has been a bit of a journey. And while I'm not displeased with the results that I've gotten, I think the process of iterating through the different designs is probably more interesting than the actual final product that I got. So let's back up a little bit and start at the beginning. So, about a month ago, when the coronavirus concerns really started to ramp up here in the States, I started thinking, like most every other engineer and hacker and maker in their garage, like, how can I help? My wife's in healthcare, and I come from a molecular biology background. So this was both kind of relevant to me and also interesting from a design problem to try to solve. I think everyone at this point has probably seen the 3D printed masks that are making the rounds on the internet. And I think this is a very well intentioned idea, but ultimately just not going to work for a variety of reasons. The most obvious reason, which everyone can kind of see right away, is that 3D printed masks are generally very rigid, and rigidity doesn't usually go very well with a compliant mask that's supposed to fit to the contours of your face. There are ways around this by adding some kind of gasket or seal around the edges or form fitting the mask to your personal face, and these can help to a degree. We'll see towards the end of the video that I ended up purchasing a used mask fit tester off eBay to quantitatively determine how well my designs were doing. And even with a very compliant soft silicone seal to my face, I was still only achieving a 67 fit factor, meaning that the ambient particle count inside of the mask was 67 times lower than outside the mask, which sounds good, but the minimum that NIOSH approved respirators must meet for a fit factor is 100. So it was still failing after extensive work to try to get a very compliant seal. So I just don't think a 3D printed mask with any kind of gasket will probably pass a real fit test. Ultimately, it was this line of thinking that led me down the particular path that I did. So I pulled out my commercial respirator and started trying to understand how they made it. So these elastomeric respirators are usually molded in two pieces. There's an internal hard or relatively rigid plastic on the inside of the mask, which has the bayonet adapter. And then that's been overmolded with some type of elastomeric, soft compliant silicone or skin safe rubber of some variety. These are 100% injection molded. You can see the ejector pin locations on the plastic. And the more I look at these things, the more just I'm blown away by the skill that is required to make a really good injection mold. Just the physics of getting all the slides and draft angles and everything correct is just, I'm in awe. But in any case, because they're injection molded, it led me to believe that I could do a similar thing, but with RTV molding at a smaller scale.
The idea behind this first attempt was a simple overmold design using something like this for the cartridge. This is the kind of standard bayonet design. This is 3D printed on an SLA printer. And similarly, here's another prototype that was in FDM, but both of these would eventually be cast out of urethane rather than 3D printing. So this was just to help create the molds. The idea is that this sits inside of a mold and is kind of suspended in place, and then you cast silicone down over it, which is why it has these holes through it to help kind of provide mechanical gripping strength. To do that, I had created this 3D printed mold. And so you can see this is a 6-piece mold. So there's 2 pieces on the top, on the inside here. Then there's a middle piece, which has the outer shape of the respirator itself. An inner piece, which pops out, and this is kind of the inside of the respirator. And then a bottom part, you can see, not a great print, but the underside to give kind of a lip to the respirator, and then the bottom. have the bottom piece, you assemble this interior piece like so, and you place this on top, and there are registration pins that allow it to line up correctly. And then this top part of the mold is designed to capture the overmolded piece. And so the way that works is there are lines here. This might not fit because it currently has silicone in it. But the idea is you capture, let's see, I think it goes like that, yeah. So you capture the piece like so, and then line up the other piece. And if this were cleaned out, this would snap together, and it essentially holds the overmolded piece kind of in suspension right above. So you can see there's a little bit of space on the underside here to allow silicone to flow on all sides and then also go through the holes. And when you flip this over, it sits down like so, and then you can pour in through these spouts as well as through the middle. So here is the result that came out of it. You can see there's the overmolded piece. This is again just 3D printed as a test, but it's captured essentially inside of the silicone and doesn't come out easily. And the overmolding is important to have mechanical attachment because silicone basically doesn't want to stick to anything except itself. And so it will not bind to this plastic very well. You can see you can kind of pull it back here without special glues to attach silicone to other things. So having mechanical fastening is important for overmolded pieces. And you can see it attaches to the cartridge like so. There would need to be some kind of gasket to make that sealed nice, but that's a future detail. And then you have, you know, a relatively reasonable mask. Now there's a couple problems with this design. I take this off. Obviously, as you can see, this is far too floppy. The durometer of silicone that I used here is 0050, which is a lot less stiff than I expected. It's basically softer than skin. It's very stretchy, it's very compliant. And so at this thickness, which is maybe, I don't know, a 1/16 of an inch, a millimeter or 3, something like that, it's just too floppy. It's too compliant. When it's pressed against your face, it immediately squishes. But the process was very encouraging, especially at the beginning when I was getting started, because it just molds very easily, and you could envision people printing out these molds without a lot of hassle, and then just pulling it off the mold when they're done. One of the things that's pretty important on these reusable respirators is having proper amount of surface area for breathing. And while this did allow commercial cartridges and large cartridges, it still was only one breathing port. So kind of in parallel to working on that design, I started drafting up a different version, which was potentially simpler. So the idea here is that it's just 2 large holes, which allows you to plug a cartridge on top. The cartridge can be, you know, any particular size, but it's just a press fit onto the mask. This gives you 2 very large breathing ports. It's simple, there's no overmolded parts, and it's just kind of ready to go. The downside is that it doesn't allow reusing commercial cartridges, so if and when those become available, you're still stuck with kind of the DIY approach, which is not really ideal in kind of hospital environments. But one of the good and bad things about this is while you're waiting for silicone to cure, you can start working on a new design kind of in parallel. I started to learn some of the difficulties of working with urethane. So the idea for this was the model that I kind of drafted it on, but then I printed the inverse model like I did with the silicone mold, and you can see the remnants of this one, with the idea that it's a 3D printed mold that you liberally coat with mold release or lacquer or acrylic or something to help seal it, and then mold release. And then you cast the urethane right into it. This urethane is a high-performance urethane from Smooth-On called Task 8. It's autoclavable, and it has a relatively high heat deflection temperature, so it should be reusable, it's resistant to solvents, et cetera, et cetera. So it's a great urethane, but as I discovered, urethane basically sticks to everything, including 3D prints, despite liberal application of mold release. So I tried this a few different times. Here's the carnage left over from one mold. Here's another one that I got out of a mold, but it basically took the mold with it and destroyed the mask in the process. So I learned relatively quickly that even when you have nice molds like this is unused, but presumably the same fate awaits it. The 3D printed molds are just too porous for urethane to be cast into unless you go through a lot of effort to seal it with epoxy or acrylic to make sure the layer lines are completely smooth. Because the nature of the urethane is just going to grab onto every nook and cranny and hold on much tighter than you expect. So instead I fell back to what you really should be doing with molding and was totally new to me, which is silicone casting the exterior mold that you then cast the urethane into. So here's a 2-part mold made out of silicone. So relatively flexible. You can see it comes apart and you've got your 2 pieces here. And this is basically just a casting of this. And yeah, the idea basically is once you have this mold created, you slot it back together. And there's a pour spout and an air spout. So you pour in here, and when it starts coming out the top, you're done. And then it creates parts that look like this. So this is in that urethane. It's a very faithful copy of the original. And it is in the urethane, and so it has all of the mechanical properties that you don't get with the 3D printed. But as I mentioned, I was working kind of in parallel. While one mold was curing, I was also working on prototypes of the next iteration, and I just couldn't give up the idea of these reusable bayonet style attachments, simply because it allows you to use commercial filters if and when they become available. And it's much more likely a hospital or healthcare provider is going to accept something that looks like this rather than something that looks, a little jankier like this. And so I came back to the cartridge style designs and iterated on a few different models. You can see here, this is an FDM one that's been coated in epoxy for casting purposes. It looks different from the prior cartridge design that it has 2 cartridges and has a little nub to hold kind of a retainer. Has a lip around the edges for mechanical fastening to the silicone. Here's the same idea, but in SLA instead of FDM, so it's much nicer finish, and this mold's much cleaner if you ignore some of the broken bits. And then here's a later iteration which has larger mechanical fastening, which was a little less fiddly than these. These small details don't mold very well. Or rather, they mold really well, but getting a good parting line is difficult. And so something like this is just a lot simpler. And it also has a bit better of a profile. But yeah, so that's the idea behind these masks. And these look, not surprisingly, very similar to a commercial mask. Now, the issue with molding and casting in silicone is that silicone's not cheap. This stuff is between $100 and $200 a gallon. And it takes a surprisingly large amount of silicone to make a casting of this size. So I printed essentially a mold container. So this is a custom 3D printed container that approximates the shape of the mold rather than casting into just a big cube like this, which has a lot of wasted silicone around all the edges. You instead cast into a custom fit, meaning that you only need like ½ an inch of silicone around any particular side. The problem though is I cast it with this, and I didn't realize this at the time, but I had super glued the bayonet adapter on, and super glue apparently inhibits the cure of this particular silicone. So all the details that are inside in essentially the critical location didn't come out, and this is still kind of goopy to this day, and it's been sitting there for, I don't know, 2 weeks now. The next design, rather than trying to get a streamlined mold like this to, aggressively save silicone, I kind of opted for a design in the middle like this. So you can see it's a simple 2-part mold that is approximately in the shape of the mask so that it saves some silicone around the edges. It's not as wasteful as a cube, but it's also not quite as form-fitting as the prior one, but it should be considerably easier to demold. So you can see here is the mold that it produced. It's got two parts as you'd expect, and it looks basically like the inverse of the master. And this is the master that went into it. And you can see I did a poor job cleaning up this particular master. There's a lot of support material and just general roughness. I did hit it with a coat of epoxy to smooth it out a little bit, but it's not in great shape, which is why the master itself is pretty rough around the edges, quite literally. But this was just a test to kind of prove it out, and I wasn't too concerned about the master being beautiful. So with this mold, I created, or I cast rather, this piece. So you can see it is a faithful replica of the master. It's in the same Task 8 polyurethane that I mentioned before. And importantly, the bayonet cartridge works as you'd expect, which is really nice. So this is basically a relatively functional prototype at this point. If I were to clean up the master and make a better mold, this would be much more cosmetically nice, but it does function. So the next step is to make the kind of silicone sealant or the gasket around the edge, because this is obviously not going to be fit to your face and provide any protection.
I'm going to interject a quick editorial note. You might be looking at this prototype right now and thinking to yourself, this looks an awful lot like a hard, rigid 3D printed mask with a sealant ring around the bottom, which is exactly something you said wouldn't work. And you are totally correct. At this point in the prototyping process, I didn't realize this wasn't going to be an easy option. And I was still thinking a thin sealant ring around the edges would work great. So I discovered later that that was not the case, and that's partially why some of the designs changed in the future. Okay, back to the show and tell.
So I'd always assumed this would be the easy part, because you should be able to just make a mold like this. There's kind of a little undercut lip underneath here. You set your component on top of that, and it sort of floats inside the mold, and then you just pour silicone down around the side and rises up the level and seals it off and makes you a nice gasket. This is the gasket that came out of it, and unfortunately I just thoroughly underestimated how stiff silicone can get when in a large quantity. So this is the really soft 0050. So it is very squishy, but when you have it on your face, it still is pretty solid, especially in this thickness. And so it's actually quite uncomfortable. And obviously this is too large for any practical use. So I think the theory works, but you would need a much smaller seal to go all the way around, which then gets back to being difficult to actually seal because you have less material working with. So I think this approach could work, but it would need a lot of tweaking and tuning to get there. And then there's also some practical concerns that this mechanical lip was not sufficient, and you can peel the silicone off very easily. So that was not great. So that brings me to the final design, which has a hard centerpiece that looks like this. And so you can see this is essentially a slimmed down version of the full mask, right? It's not as thick. It basically only has the cartridge, the little nub on the top to retain kind of a strap for your face, the bayonets. And then rather than trying to use kind of mechanical fastening around the edges, I just punched a bunch of holes directly through the mask to help retain the silicone. And so this is the only hard part in the mask, and everything else will be cast out of silicone. So I went ahead and cast myself a full mold with 4 different pieces. So this is known as a gang mold, where you can essentially cast multiple pieces at once. And the idea behind doing a gang mold is that you're already going through all the work to set up one master and do the parting lines and get the bottom and the top and the pour and all that. So you might as well do multiples at the same time. And once you're done with that, you get parts that look like this. And so this mostly worked. There are some issues. There is some air entrapment at the top of the cartridges. So if you think about it and look at how this is set up, when you pour it in, the silicone or the urethane goes in here or here, so that's where the air can leave, and you end up getting bubbles kind of at the tips of all the cartridges. So what I need is an air vent kind of going to each of these to let that air out, because that's a perfect place for bubbles to be entrained. But otherwise, it came out really nice. The flashing's not too bad. It cleans up very easily. It's a nice hard piece. And with a little bit of tweaking, this would actually generate some pretty nice parts. With the hard section complete, I moved on to the silicone section. And much like the earlier molds, like this mold that was 3D printed, I went ahead and 3D printed the silicone part. This is easier, faster, and cheaper than doing a silicone mold for the silicone components. Silicone doesn't really stick to anything except itself, and so it will happily not stick to plastic, even 3D printed plastic, especially if it's been coated with some kind of epoxy on the inside to make it a little smoother. So there's really no concerns with using 3D printed molds for the silicone part of the mask. So there's a bottom section that has the bottom lip of the respirator, kind of an internal plug that has the corresponding geometry that goes there. And then a top piece that sits on top, and this clicks into place if you push on it. These two holes here, I don't have them up here right now, but there are two plugs that fit inside of here, and those are used to hold onto the cartridge part. And so the way this works is you clamp this down like so, and then you sit this previously cast urethane part right here. And the way it's designed is there's a nub, and that sits right here and keeps it just slightly raised above the surface. So there's space underneath and around on all sides. And the idea with that is that as you pour in silicone, it goes over the part and also goes under the part to give kind of a full overmolded. And then you set this on top like so. And this would click into place if I was actually casting it. And then you can see here that this kind of just floats inside. And you put the plugs on, pour the silicone from the top, kind of get the air bubbles out. And when you're done, you get a respirator that looks something like this. So this is done in clear silicone. This is called Sorta Clear 18. So it has 18 durometer. It's sorta clear as the name implies. And this is skin safe silicone. And yeah, this is essentially close to the end product. This is 99% of the way there. There are some issues that need to be resolved. As I mentioned before, the bubble entrapment. This Sorta Clear is actually too rigid for the mold that I made. So the thickness here is too thick, and this is actually remarkably stiff to go on your face. And so this is pretty uncomfortable, but you can get a good airtight seal. The overmolding aspect worked really well. This is very firmly held in there. You really can't get the old overmolded part out because it's so completely molded. And importantly, you can attach the filters like so, and it makes a pretty good seal when you do. So I went ahead and did another casting where I replaced the plug with something smaller, and I used my other silicone, the 0050 silicone, and came out with this. And I added some white pigment just to make it look nice, but this is essentially the same as this, the same internal piece, just with a different silicone and slightly thinner walls. And this is much more flexible relative to the other one. You can just see, you know, visually that this is a more compliant silicone. And this is extremely comfortable on your face. It's almost a bit too compliant. I think something a little stiffer would be nice, so beefing this up a little bit. But it seals very well to the filter. It has the same mechanical properties. It's just more pleasant to be on your face at any particular time. So this is the end product. This is essentially a month's worth of obsession and work to get to this point. I think it's interesting to see where I started, which is kind of this, and then an intermediate point, which is something like this, and then getting to a functional product, so to speak, which looks like this.
Now, like any good scientist, you really need data to validate your claims. And so I didn't want to just build these prototypes and throw them out in the world with no kind of data behind it. So to that end, I purchased a surplus 1999 military mask fit tester. It was last calibrated in 2016, so I'm assuming it's still in good working order. Everything seems to check out. The self check is fine. And with this, I can actually test to see quantitatively how well my mask prototypes work. So, the way these machines work is by drawing a slight vacuum on two different tubes, one that's open to ambient air and one that is connected to the interior of the mask or respirator that you're testing. It then samples the particle counts from inside and outside your mask and compares the two to determine a fit factor. Here I'm loading a wick that has been soaked in 99% isopropyl alcohol. And my understanding is that these machines use the isopropyl to condense particles out of the air and then resuspend them in a way that a laser can detect it. The machine has two operating modes. The first is the real time particle counter, and this pulls, I think, every second or two and gives an average of the particles per cubic centimeter inside of the mask. So you can see the values jumping around here as I'm trying to get everything seated on my face. I still don't have the straps really set up correctly, and so it's a little fiddly to get everything exactly where it should be. But you'll see that it jumps around quite a bit. It goes from relatively low values up to relatively high values. And for comparison, my ambient particle count is about 2,000 particles per cubic centimeter. The other mode is a fit test mode, and the idea here is you perform a number of actual exercises like standing up, sitting down, walking around in circles, looking up, looking down, different things to move the mask like you would normally move it in a day to day operation. And during each of these exercises, it's comparing the ambient to the internal particle counts and will give you an overall ratio or a fit factor. I just had it set to one exercise and I sat very, very still, trying to get essentially the most ideal situation possible. And despite that, I got a 67 fit factor. It's hard to know exactly what went wrong. My kind of anecdotal feeling is that due to not having an exhale vent and only having one cartridge, you can feel the edges of the mask puff up slightly when you're exhaling because there's more pressure inside the mask. And that's probably when a small leak is occurring either around the nose or the bottom of the chin. The other practical point is that I do have facial hair and it is not an approved CDC facial hair. And so that is definitely leading to a worse fit factor than I might otherwise have. So that's kind of where I'm at. I have a respirator design that almost passes a fit test, but not quite. I think with a little bit more time and effort, I could probably get it working. I've learned a truly ridiculous amount of information about how RTV, silicone, and urethane molding works, how hard multi part injection molds can be configured. Like, it's really been a crash course in a whole bunch of techniques that I had zero experience with before. So I think it was a really good learning opportunity. I do wish I had slept a little more while working on this. The feeling of needing to get this done for a pandemic was terrifying and kind of exciting, and, well, something I don't think I really want to do ever again. This video is silly long, so thanks to anyone who's still actually here listening to me talk. I hope seeing kind of all the different prototypes and how I went about thinking about the different kind of design revisions between each of them, I hope that was interesting to someone. And thank you all for watching. I'll talk to you later.